So next, this is a rule on joint probabilities or random variables of random variables. What is that? That probability of x taking the value x given that y has taken a value y is equals to probability of y taking a value y given that x has taken the value x multiplied with probability that x has taken a value x divided by probability that y has taken a value y. So I will not go into the derivation of this rule or try to visually represent this rule because this is very complicated like derivation to reach up to this point. But this is a very important rule for statistical learning concepts, probabilistic learning concepts. All right. Next, we'll be seeing one algorithm that does some form of machine learning, which is completely based on this rule. Okay, so if you're interested, you can go ahead and look on internet or use some book to see the derivation of how we reach up to this formula. But as of now, just try to understand what it is written, and that will be good for us. And what it says is that x taking a value x given that y takes a value y is equals to y taking a value y given that x takes a value x when multiplied by probability of when x takes x and probability of when y takes y. This is what this rule is. Okay, this I'm only trying to explain what is written, how it has been derived, or what is the inference behind it, or how we can visually understand it is very difficult. As of now, it has a complete derivation behind it. But let me give you like one inference of how this rule is useful for us. That let's say for certain values of let's say we have a relationship from x to y. If there is such a case, there is such a variable that we have a relationship from x to y, and if we want to know the relationships from y to x, because these are not the same things in all cases. All right, the relationship that x has with y may not be the same as the relationship that y has with x. It could vary largely, very largely. Okay, so this rule is useful when we have one of such relationships and we are trying to identify the other relationship. This is where we use this rule. Just try to remember that whenever we will be having such a situation where we have relationship from one random variable to another and we need the inverted form of relationship, i.e. the relationship from other random variable to the first one, we can use this rule. Just try to remember that, and when we'll require, we'll take this rule from here and use it. Okay, as of now I do not want to go into the explanation of that because that will take a lot of time and we are already short on time. And do you need 2 minutes to digest what we have discussed till now? I think the probability of getting a no for such an answer is increasing day by day. I should try to learn something from that. Great. So moving ahead, we'll talk about independent random variables. That is very similar to independent events. Here, the probability of x taking a value x and the y taking a value y will be equals to probability such that x takes x independently of y takes y, since both of these are independent variables. Or I can say that the underlying events or underlying not experiments, but underlying events are independent. So variables are nothing but collection of outcomes of experiments. And for a given event, when we collect such different outcomes and we give them a certain number, that is a random variable. Okay, so ultimately how a random variable will behave also depends upon the parameters on which the experiment was performed, or the event which we are trying to learn or understand. Okay. Now, similar to probability distributions, we also have something called probability density functions, which are relevant for continuous random variables. Till now, we were discussing discrete random variables, which will have values from a very closed set of numbers. Okay. However, in case of continuous random variables, they can have a lower bound and an upper bound, but they can take any value within that range. So it is a continuous variable. You understand the difference between continuous and discrete variable, right? So given this particular axis, if let's say x can take only these values, then it is a discrete variable. However, if x can take any value on this scale, so let's say this is 1, 2, 3, 4, 5, 6. So I decided some values. They may not be exactly 1, 2, 3, 4, 5. I have decided some values, and if x can take these values only, then it is a discrete variable. However, if it can take values like 1.14579, or let's say 2.34, or let's say 7.62 or something like that, then such a variable is a continuous variable. All right. So in a continuous random variable, what we'll study their density functions. So where the maximum density lies, depending upon the probability of values that it can take. So such a function is defined like this, and this is the property of probability density function. We will not study them more because in computing, generally what we are interested in is discrete functions, discrete variables only. It is just to give you like a sense of that there are also there is a continuous continuum out there, which is not completely related to discrete variables only.